work we've been doing on fractionation of gas and pyroclastic eruption formation, but also give you a little bit of background, because what we're really looking at here is gas that's coming from the interior, of course. So this is some of the material that may work its way to the poles, either historically or even today, or maybe some of this earlier volatile exsolution, not from Pu'uo, but directly from those on the moon, may have reached the poles and be preserved there in a historical record. So a critical question is, in fact, okay, let's just do it here. Okay, I'm going to have to give me the code here for... Yep, I got it. So there's a whole series of reasons why studying these pyroclastic eruptions are important. The volatile content, understanding the volatile content of the magma for individual eruptions for the planet as a whole, like the moon or Mercury, for example. It's interesting, too, from fractionation processes. There's a lot of fractionation processes that are going on here, too. If we want to understand the total volatile content, we need to actually understand what those processes are. The behavior of magma, the style of eruptions, these are all critically important. And you can work your way down to looking at the nature of eruption processes, particularly the fountain optical density, which is really well illustrated by this Pu'uo eruption here, where you can see the variation in optical density from low density cooling out here to high density into the interior. And then, of course, modification processes, and finally into resources that can be really critically important for the moon. Now, Lisa Gaddis has spent a lot of time and working with a lot of us here in the field to map out the distribution of these types of deposits. And clearly, they are closely associated with lunar mare deposits, as you can see here, the yellow dots, etc. They're also associated with not just the mare, but the graben around the edges of the mare. Some of these graben may be, in fact, from flexural deformation, but others we'll show in a minute are really related to dike emplacement events. And, of course, as you heard earlier today, perhaps if you're in the other room, Lauren Joswiak pointed out how many of these pyroclastic deposits are associated with shallow intrusions of floor-fractured craters. Now, 3 different types of deposits have been described based on Lisa Gaddis's and others' work, okay? And bottom line here is that they're smaller, really isolated deposits. These are less than a few kilometers, tens of kilometers perhaps in diameter. The eruption styles seem to be related to dike and sill emplacement, okay, where you get near the surface and then there's gas exsolution, formation, etc. And then these eruptions, this is kind of classically what we see in the crater Alphonsus, which I'll show in a minute here. Then there's the intermediate scale circular deposit. The best known, in fact, only really well known here, is 154 kilometer diameter Oriental dark ring, which has a vent in the middle. This seemed to be a single eruption from a shallow dike fractionation processes, production of excess volatiles and eruption to produce this type feature. And then there are these large regional deposits, greater than 1,000 square kilometers, which typically are shown here: Aristarchus Plateau, Apollo 17, Rima, Bode, a whole host of these other ones, generally in the equatorial region of the moon. So these are a little bit enigmatic. In some cases, Aristarchus will show in a minute that the cobra head, the large sinuous reel there, may be largely responsible for the pyroclastics there, but others don't have that same kind of thing, and so that's going to be the topic of some of our discussion today. How do you get these large deposits without similar types of vents? So what are the sources of volatiles? We've heard a little bit about this earlier today from Catherine's talk, etc. The volatile content of the mantle source rock, of course, as it begins and works its way towards the surface. There's also a process here that's the key driver, of course, what it was originally. Then how does it get out of the magma? Well, there's a dike tip low pressure zone. As the dike propagates, even at these great depths, it creates a low pressure zone in which gas can actually exhaust from the magma in that low pressure zone, even though the overburden pressure is really large. Okay, so this, in fact, can cause collection of exsolution products and propagation of those at the tip of the dike. And typically, when these get to the surface, there's an eruption of this before the effusion of the lava that's involved in the eruption and the main form of the dike itself. A third is shallow pressure-dependent gas exsolution. That's the normal kind of thing. With overburden pressure decreases, you, in fact, start exsolving gases, SO2, CO2, sulfur, chlorine, fluorine, et cetera, okay? The second one is, on the moon, is the shallow pressure-dependent chemical reaction, onset of smelting products, CO at about 40 megapascals, which is about 10 kilometers. So both of these combine in the shallow crust region here to give you a significant amount of volatiles. And then, of course, we have shallow fractionation processes. While you're doing this, you can actually collect this material if the dike stalls, and it can build up a lot more than is, in fact, just in the magma itself. So it's a fractionation process of essentially an addition of volatiles, which produces even more volatiles in the dike tip, and then finally volatile losses during eruption. You can see here in the case of Pu'uo how much gas is actually emerging to the surface there at the top of the plume. Now, the shallow fractionation processes can be really critical. We know these exist on the moon because we see examples in this block diagram here of magma source, simple-minded here. The dike propagates, dies a heat death here, nothing much happens, but when it gets close to the surface, between dying a heat death and actually getting to the surface and erupting, we see shallow stalling of the dikes. You can get fractionation associated with this. Say the Mendeleev crater chain is a good example of a dike that's propagated to the near surface. Exhaled volatiles, the gases have come out and caused individual pits along the surface. On the other hand, here you can have actually volatiles coming to the surface to create, in the case of Rima Peri 5, where you have propagation, you actually have pyroclastic cones, more likely to be strombolian-like cones along the surface as well. And while the magma is sitting here, you can, in fact, get a lot of gas fractionation and build up the volatile content with interesting consequences. So when we look at eruption styles, then, we have strombolian, Hawaiian, and Pallenian. Strombolian is essentially episodic gas slugs coming to the surface and producing deposits in the near field, whereas Hawaiian tend to be continuous gas loss as the magma is coming to the surface to produce, again, optically thick and optically thin portions of a plume. And then, of course, Plenian, which is ingestion of gas as atmospheric gas as the plume comes to the surface. And, of course, this isn't likely to happen on the surface of the moon because, in fact, no offense here, but there are very few molecules, okay? They're there, okay? They're there. I don't want to insult anybody here, but they're there. Okay, so what do we have? We have, essentially, in this kind of environment, the regional dark mantle deposits focused on pyroclastic volcanic eruptions and work we did in a long time ago. Basically, what happens is as the gas comes to the surface, it does not ingest any atmospheric gas. It essentially is a foam that gets to the surface. So foam is bubbles in a magmatic foam, okay? And as the bubbles disrupt, okay, they break up and they form an expanding plume, if you will, concentric plume as the gas comes out. As the bubble walls break up, they form the little glass particles, the little particles, magmatic particles, okay, which then are accelerated by expansion of the gas cloud. As this expands, it's pushing these gas clouds out by the expanding gas, accelerating them. And of course, when the gas cloud decreases in density sufficiently so that the particles are no longer coupled to the gas, they are not being pushed by the gas anymore, but they're on ballistic trajectories. So they're just gone, okay, to some distance related to the magma volatile content. Okay, so when we do these, we can see and map these out. We can actually relate it back to the gas content, if you will, okay? And of course, the smaller dark halo craters, which we'll take a look at in a minute, are really dikes stalling in the near surface, building up gas foam and then exploding to produce these kind of like volcanic eruptions. And in I'll skip this one because we already talked about dike tip volatile exsolution. But here at Apollo 17, we were really lucky to really actually examine one of these deposits in detail. Work done by Kathy Whiteson while she was at Brown really showed how we can actually look at the plume, this expanding gas plume, and relate different types of pyroclasts and particles associated with these eruptions to the optical density in the plume itself and the deposits, both proximal and distal deposits. Okay, so I really encourage you, if you're interested in this sort of thing, to go to these papers here because they lay out in detail the relationships among these types of things. So bottom line is we can get different kinds of crystallinity. So the key point here is that the glass particles themselves, like the orange glass beads here, are in this optically thin portion. They're actually out in the optically thin portion. And so they, in fact, quench and cool very rapidly, whereas the material in here, in fact, continues to crystallize because it's in the optically thick portion of the cloud. That would be in this area here, which is all red as opposed to darker in the thinner portion. And so they stay there and they crystallize and, in fact, can fall back in and become part of the lava flow again. So bottom line here is when we take a look at these Alphonsus type features here, okay, they seem to be Volcanian type eruptions, but are these dikes that are coming all the way from the interior or are they localized dikes, okay? So this is also a floor fractured crater. So in fact, as Lauren Joswiak has shown, this is likely to be a sill eruption, a sill emplacement event here, and as the sill is emplacing, okay, it reaches maybe hundreds of meters thick, and then starts to undergo or continues to undergo gas exsolution. So it builds up the foam at the top of this sill. And when the sill cracks, when the cover cracks here, if you will, that's when you get these types of pyroclastic eruptions. So again, this is a new development based on Lauren's work where we'll be able to see and map out this evolution of shallow gas exsolution to see what the impact is on these dark halo craters here and how they're linked. Okay, so if we then take a look at these, this larger feature here, this dark halo here, in the 154 kilometer diameter approximately feature here, this dark ring, okay, nobody knew what this was until we found, I think, conclusively this vent right in the center of this feature here from the Clementine data. And we were able to see, in fact, and model this as a dike emplaced into the shallow crust, essentially volatile fractionation and exsolution and formation here and buildup until, in fact, it reaches a pressure there that is greater than the overburden pressure and the rock pressure. And then it propagates through to create essentially an Ionian-like plume. If you were to see this from a distance, like from the Earth, you would think you were on Io, okay, because it's one of those big plumes like you see on Io. They work exactly in the same manner. And then, of course, it collapses down into this void to produce what we see here. So this is another option for this intermediate type of feature. But what happens here with these continuous eruptions on the moon? We really want to understand what these continuous types of eruptions are with these regional dark mantle deposits. And when we take a look at these, we find, in fact, that for this Aristarchus one, we have a really kind of smoking gun candidate here, Cobra Head, which is, in fact, this very large deposit here. And probably the pyroclastics here, this represents extremely high fusion rates with an optically very thick cloud here. And so the pyroclastics are likely to be related to these deposits in the surrounding area from these continuous eruptions. On the other hand, when we look here, we don't have sinuous rills for these other ones. So what's going on there? When we look, what we find, in fact, is in a lot of these areas, these linear features here, the absolutely excellent lunar reconnaissance orbiter data from the camera system, from the laser altimeter and others are just incredible for doing this kind of mapping. And we see lots of evidence for linear rills and linear rill-like features in here. So we're thinking these may be shallow dike intrusions. And if you just do the quick math here, if you take a look at these, they're 100 kilometers in diameter, et cetera, if you will. This would imply 403 meters per second ejection velocity from a single vent. But in fact, this doesn't work, because when you do the math on 2,000 ppm, 700 ppm, 325, add all these up, you're only going to get a 10 or so 20 kilometer diameter range. So something like a 12-fold gas exsolution must occur. That's why fractionation is really a critical parameter here. We think that's really important. I won't give you the details of the math, but when we do this here, we can in fact get 176 kilometers with a gas fractionation concentration factor of 22, and so a lot of gas fractionation is going on. So this is really something to keep in mind. And when you, in fact, go to the Apollo 17 area then, the gas concentration, a take-home message here for regional pyroclastics, gas concentration in foams at the tops of these dikes, these shallow dike intrusions, should have been common on the moon, and it would have been easy to produce meter-thick pyroclastic deposits over 100 kilometers times large areas, okay, like we see for the regional dark mantle deposits. Now, this is good news because we're beginning to understand the process. It's bad news because what we really want to do is use the range to back out the volatile content. So this tells you that the fractionation processes and the volatile buildup is such that you can't do that easily, okay? So we have to keep that in mind. However, there's good news, okay? The good news is that, in fact, these things are made up of these pyroclastic glasses, and stick around for the next talk because Shuai Li will tell you in the, in fact, M-cube data, the surface hydration using M-cube data and an improved thermal correction really provides evidence for regional variations and, in fact, what looks like the water content, if you will, the volatile content, and he'll show you in detail how these regional variations may indeed help us to actually map out where some of these linear rills are that may be more covered up by the pyroclastic deposits. So a lot of developments, lots of really important information about what's going on in terms of volatile exsolution from the interior and derivation. And we're beginning to get the equations to crack the code. Stick around for the next talk. It's really good. Thanks.
I would have cut you off, but you were spending your time advertising the next talk.